Love it. Okay, we're going to get into it. So today we're going to talk about the Hardy-Weinberg equilibrium, so you can follow along. This is the last topic we're doing for the year. I didn't even write that right. Oh my God. Okay, let me try again. Hardy-Weinberg equilibrium. Okay, from now on, we're going to just call it HWE. So we don't have to keep writing. Yeah, equilibrium. RIUM. All right, so what this is it's a mathematical measurement of evolution. So what does that mean? What does that mean? So it's a way to measure changes in genotypes over generations. Okay, so remember a genotype is like this, right? This is your genotype. And that genotype is going to produce something called a phenotype, right? That's what we actually look at, what we can see. So the phenotype here would maybe be brown eyes or brown hair. Okay, so this is the genotype. It's going to make a phenotype, which is like something you can physically see. So, so for a population, why you would want to do this is there's some questions you'd want to ask. Is the population getting taller, shorter, more brown hair? So right, those are some phenotypes, right? So is what's happening to this population? Is it getting taller over time? Is the population getting shorter? Is brown hair becoming more prevalent? You can also use this to track, is there more disease? Like a particular disorder, like the one we're going to talk about today is more what's called sickle cell anemia. So you can measure, you can apply mathematics to determine if these traits are becoming more or less prevalent in a population. So some populations in the world over the last 50 years have been experiencing what's called a microevolution, in that they're getting taller. For whatever reason, the average height went from being, 5'10" for males to now it's 6'1". So what's producing that? Well, there has to be a change in the prevalence of some genotype that's getting picked up. The United States, the population's been getting shorter. So we're losing some of the tall alleles, and so we're having our phenotype is getting shorter. So this is just a mathematical way that you can say, okay, this population is evolving. It has changed its phenotype. Okay, so let's do an example. So in addition to measuring changes in genotypes, we can also look at changes in alleles. Remember, that means individual letters inside of a genotype. All right, so this is our gene pool. Okay, in our gene pool, we'll call this generation 1. In our gene pool, these are our individuals. We've got a homozygous dominant individual, a couple of heterozygous. We've got another homozygous dominant, another heterozygous, and we have one homozygous recessive. Okay, so based on this, we can determine genotype frequency and we can also determine allele frequency. So let's do genotype frequency. Okay, we have 1, 2, 3, 4, 5, 6 individuals in total, right? How many individuals are homozygous dominant? 1, 2. So 2 out of the 6 are homozygous dominant. Okay, how many individuals are heterozygous? 3, good. So 3 out of the 6 would be heterozygous. And then what is our genotype frequency for our homozygous recessive? 1/6, very good. Okay, so that would be the genotype frequency. We could also break those letters apart and look at allele frequency. All right, how many capital A's do we have? 1, 2, 3, 4, 5, 6, 7. So 7 out of the 12 alleles, because right, we had 6 genotypes, which gives us 12 alleles. So there's 7 12ths are big A's. All right, how many recessive A's do we have? 5 12ths. All right, so those are our frequencies for this current population. Okay, so let's fast forward a few generations. Let's look at generation number 4, right? So we went from the first generation, they've mated, had offspring, mated, had offspring, mated, have offspring, right? So now we're at generation 4. And let's take a look at how the gene pool has changed. Okay. All right, so let's do another gene pool. Okay. Now we still just have 6 individuals, so our population hasn't grown, but everyone in the population is heterozygous. So we can do the genotype frequency. And this will be easy because, right, we have 0 homozygous dominant. We have 6 out of 6 heterozygous, and we have 0 homozygous recessive. All right, allele frequency. Okay, for our big A's, we have 6 out of 12, and for our recessive A's, we have 6 out of 12. Okay, so has this population changed between has the frequencies of alleles and genotypes, has it changed between the first generation and the 4th generation? Yes, it has changed, right? We went from we used to have a recessive individual, now we don't have any. We used to have some dominant, now we don't have any. They're all heterozygous. So this isn't a huge shift, but let's say that this heterozygous coded for tallness, okay? Now all the tall is gone. So this population, there wouldn't be anyone tall. So it's gone. Sure. You think your phone rang, Greta? Okay. All right. So this is what Hardy-Weinberg is going to do. It compares the frequencies of genotypes between generations. But the issue is we can't just look at a population and determine what the genotype is, right? We can't see their genotype. We don't know if someone is homozygous dominant or heterozygous. They look the same. They both have brown hair. We can't tell which one they are, okay? So that's why we have to use the math problem as kind of a way to go about it. So before we do the equation, let's talk about what can cause evolution. So what are 5 mechanisms of evolution? Okay. We have number 1, something called gene flow. This is, right, people moving out, people moving in. This is migration of alleles into or out of a population. So that's gene flow. All right, another mechanism of evolution is mutations. These have M-U-T-A-T-I-O-N. Okay, so you learned about these. This is a spontaneous change in alleles, right? You might have said, let's say you might have been GAATTC, but for whatever reason, when you did mitosis, there was an error, and now you're GTATTC. Right. We have a swap, and that could have been swapped to a C or a G or something else, but yeah, so it's a mutation. And those happen randomly and they're spontaneous, and if it was beneficial, if it produced a beneficial trait, chances are it's going to be picked up for the next, it'll be continued to be copied. It'll increase the success of that individual. All right, we also have natural selection. This is what Darwin was famous for. This is when the environment decides. So the environment decides successful traits. So if you have a certain type of beak, maybe if your beak is really long and pointed, and in the environment that you live in, you know, a pointed beak is advantageous, then that's going to be a successful trait. So you're going to have offspring and pass that trait on. If in that environment you didn't get a nice pointed beak and you had more of a short, blunt beak, and you can't access the food, you're never going to grow into adulthood. You're not going to have offspring, and so that trait's not going to get picked up. So that's when nature decides. There's also something called sexual selection. This is when there's preferential mating of certain phenotypes. You see this in birds a lot, right? Anybody know the difference between a male cardinal and a female cardinal? A male cardinal is red and a female cardinal is brown. So with sexual selection, especially in birds, the male birds always have really gorgeous feathers, like the peacock. Those are only male peacocks have those huge feather plumes. So they'll have certain traits that'll actually give them a disadvantage for surviving predation, but because it makes them more likely to find a mate, they're going to take that risk. So that's sexual selection. And then the last mechanism is something called genetic drift, which I think is all the other names kind of match what the mechanism is. This genetic drift, I don't know, I'll explain it, but I don't think the name of it makes sense. Okay, this is when genes / alleles, remember alleles are your genes, okay, your genes and alleles survive due to chance. So due to chance, I'll finish this, not because it wasn't a good or strong gene. Okay, so what does that mean? All right, you're walking down the street, walking down the sidewalk, and as you're walking, you could be stepping on, lots of little ants. Okay, so when you step on that ant and you kill it, you've taken that ant genes out of the population. So you have removed the alleles of that individual ant out of the ant population. There was nothing wrong with the ant's genes. He just happened to be in the wrong place at the wrong time. So his alleles are gone. This also happens with like natural disasters, right? There's nothing wrong with the genes of the people who live on the coastline and get hit by a hurricane, or who are just minding their business out in Kansas and they get killed in a tornado. Their alleles are now out of the population, but there was nothing wrong with the alleles. It's not like they were sickly or not good mates or something like that. They're gone due to chance. That is called genetic drift. So this would be like a natural disaster. So if there's a big fire in an ecosystem and kills a bunch of organisms, it's not that those organisms didn't have the right traits for that environment. They did. It was just someone started a fire and burned the place down, right? So the whole ecosystem went. And so a lot of alleles would be lost from those organisms that would die in the fire. But they were fine. Okay, good question. Natural selection matches the organisms to their environment. So over time, the organisms are going to be best suited for the environment that they're in. Genetic drift is just a spontaneous deletion of organisms. It has nothing to do if they were good in that environment or not. They've already been naturally selected for, right? The ants that live here in Indiana have been naturally selected to be good at surviving Indiana weather. But what they aren't ready for is my random walk I took this morning on the sidewalk. Okay? There's no way to get ready for that. It's just, if genetic drift happens to you, it happens to you. All right, so these are all the ways that evolution can happen. And right, we're talking about microevolution. A lot of times when kids think about evolution, they're talking about the creation of man. And that's not what we teach in high school biology. We don't go that far back. We're talking about how how bacteria pick up antibiotic resistance. We're talking about microevolutions, how humans are getting taller, shorter, how microbes are becoming resistant to antibiotics. So we're talking about stuff we can quantify. So it's not looking at large scale. We're looking at like this is the mathematical change in a population. Okay, so that's kind of so let's talk about the equations we're going to use. So what are these math equations? We have two that we're going to use. And these problems are honestly kind of fun once you know how to do them because it's just algebra. So, and maybe you're like, I hate algebra. I'm like, well, you'll like this algebra because it's biology algebra. It's easy. All right, so we have this first equation. And this is going to be used to get our allele frequencies. Right? This is called P plus Q equals 1. P stands for the dominant allele, and Q stands for the recessive allele. Okay, so this is your dominant, this is your recessive. All right, there's a second formula, P squared plus 2PQ plus Q squared equals 1. All right, this is for our genotype frequencies. This is how we can get our genotype frequencies. So remember our P was our dominant allele, so our P squared just means 2 dominant alleles, so that's our homozygous dominant genotype. 2PQ, remember P is our dominant and Q is our recessive, so this is going to be our heterozygous. And then Q squared would be 2 lowercase, 2 recessive. All right, so this is the formula we're going to use. And what that means is all of the dominant and recessive alleles have to add up to 100%. So it might be 75-25, it might be 50-50, it might be 25-75, but they're going to add up to 100%. And same with this one down here. For our genotype frequencies, our homozygous dominants plus our heterozygous plus our recessives are going to add up to 100%. So it could be 25-50-25, it could be 50-25-25, you know, it could be 25-25-50, whatever it is, they're going to add up to 100%. Okay, so let's do an example problem. Show you another notebook. All right, so this is the problem we're going to do. Okay, so it says sickle cell anemia is a condition caused by the inheritance of 2 recessive alleles designated little a. 2 million African Americans, or 1 out of every 12, have the sickle cell trait, not train. Trait. Calculate the following. Okay, so we're going to calculate the frequency of the genotypes and the frequencies of the alleles. But this is the problem that we're going to use. For all these Hardy-Weinberg problems, this recessive genotype is always our jumping off point. So our problem's always going to begin with giving us our Q squared. So in this case, our Q squared is equal to 1 out of 12, and we're going to reduce that down into a decimal. So let's do the steps. Okay. So let's see what we got so far. We started with our little a is equal to our Q squared is equal to 1 out of 12, which is equal to 0.0833. All right, so let's write the equations up here as a reminder, and we'll cross them off as we do them. So we're going to find each of these different variables. So the first thing we just did, and the problem gives us this, so this would be your step 1, would be find Q squared. Okay, so that's what we just did. So we're done with Q squared. Okay. Yeah. Yes. It doesn't matter. Just be consistent. If you're going to use 4 decimal places, do 4 decimal places. If you do 2, use 2. It really doesn't matter. Okay? Yeah. Okay, so that's our first step. So now we know what q squared equals. Q squared equals this. What could we find next using these two equations and your knowledge of algebra? What else could we find? All right, well, if we can't find P yet because we haven't found Q. So we could find Q. How are we going to get from Q? Right, we're going to have to square root it. So we're going to find Q, which is our allele, right? This is our genotype. This is our recessive allele. This is our recessive phenotype. Okay, which is equal to Q, which is equal to the square root of Q squared, or the square root of which happens to be okay, then let's mark that off in our formulas up there. All right, so now we have Q, so now what could we find? P, right. So we could take, so let's find P. That's going to be our dominant allele, or P, and that's going to be equal to 1 minus Q. Okay, that's going to be, I think, or close enough. Okay, so we got P. Okay, we have P, we have Q. So really we could do everything now. What do you want to do next? We just did P, so let's do P squared. So we've got P squared is going to be our homozygous dominant genotype. We already got the dominant allele. Okay, so P squared, so this was P, so we're just going to plug that in. That is 0.5059. Okay, and then our last step is finding our last genotype, which is our heterozygous genotype. So that is our 2PQ. So we just have to plug in. So we're going to take 2 times our P, which was 0.7113, times our Q, which was 0.2887. And that gives us 0.4107. Okay, so these are all in frequencies, and sometimes the problem will want you to keep them in frequencies, which means decimal, and sometimes they're going to want you to convert them to percentages. So let's look at these numbers with percentages because I think that makes a little bit more sense. So let's do all of our, all right, so we've got our alleles, and we'll have our genotypes. Okay, so let's see, what percentage of our dominant allele do we have? Can you convert that to a percentage? Right, 71% of the alleles in this population are dominant. What about recessive? 8.33. Okay, that's for our genotype. We're doing just the alleles. So our alleles would be our P and our Q. So it'd be 28.87%. Okay, and do these numbers add up to 100? I mean, just looking at this, right? Just right here without doing the decimals, so this is 99%. So that's pretty close, considering there was some rounding. 0, carry the 1. Yeah, I think that's exactly 100. Okay, so our math works out. So in this population, 71% of the population has dominant A's, 28% have recessive A's. Okay, let's look at our genotype percentages. What percentage of the population is homozygous dominant? Very good, 50.59%. What percentage is heterozygous? Good, 41.07. And then finally, what percentage is homozygous recessive? .33%. And once again, this should add up to about 100 because we rounded. So this, and it does. Okay, so this is our first quantification to tell if a population is in Hardy-Weinberg equilibrium. Equilibrium meaning no change is happening, there is no evolution, or is this population out of Hardy-Weinberg equilibrium? We'd have to have another generation to compare it to. So this would be our numbers for the African American population, and like today, it's 1 in 12. 50 years from now, we could see what the prevalence is again, and we could compare those two numbers to what we just calculated today. And then we could see, is that trait evolving in the population? Is it becoming more or less prevalent? Are these numbers changing? Because right now it should be 50% of the population is homozygous dominant, 41% is heterozygous, and only 8% has the disorder. But maybe in 50 years, these numbers shift a little bit. And this is now 4%. So what would that indicate to us? If we went from 8% to 4%, are we in Hardy-Weinberg equilibrium? No, we would not be in equilibrium. If there's a change in allele or genotype frequency, then that population is out of equilibrium and is experiencing evolution for that particular trait that you're investigating. Does that make some sense? Okay, so all of these problems are done in the same way. The problem is going to give you Q squared, and then you're going to find the square root of that, and then you're going to subtract it from 1, and then you're going to square that, and then you're going to 2PQ it. Okay, so these are the same steps. It's just the numbers you're starting off, you know, it's not always going to be this, but it's the same 5 steps over and over and over again. All right, I'm going to stop the video. Any questions on that? We feel okay. All right, I'm going to just stop recording this, and then I'll go back to the